Hello friends, in this practical we will cover the practical number 7, that is test and verify the truth tables of basic gates and the universal gates. And for this practical purpose we are going to use the online simulator software, that is circuit verse. Now this simulator software is specially designed for the digital logic design. Now when you Google circuit verse, then you will get this window. Now in this window first of all the circuit elements. Now input elements are there, that is to give the inputs, that is 0 or 1. Then next one is your output elements are also there to observe the outputs. Then the various logic gates are available, that is AND gate, then next OR gate, inverter, then XOR gate, then NAND gate, NOR gate and XNOR gate, then decoder, multiplexers, then sequential elements. These all the elements are present in the circuit verse software. Now first of all, for this practical our objective is to test and verify the truth tables of the basic gates and the universal gates. Now first of all, give the title to the project, suppose logic gates. Now the title for the project is the logic gate. Now to test and verify the truth table of logic gates, first of all select your NOT gate. Now when you select your NOT gate, then we have to give the input to the NOT gate. Now suppose now your input is present in input tab. Now connect your input to input of your inverter, and similarly in output one output element is there which will give or which will show the output, and when you connect the output of your inverter to that output element, then you will get the output. Right now let's verify the truth table of our inverter or NOT gate. Now when input is 0, then your output is 1, and similarly when input is 1, then output equals to 0. Means suppose consider your input is A and your output is Y, then the Boolean equation for your inverter or NOT gate is Y equals to A bar, means your output is inverted version of your input, means when your input is low, then your output is high. Similarly when input is high, then your output is low. Now this is the truth table for your NOT gate. Similarly we will check the truth table for the another gate. Suppose next gate is our AND gate. Now when we will select the AND gate, now for AND gate total number of 2 inputs are there, so go in input tab, then select 2 inputs, that is suppose this one is our first input and this one is our second input. Say this input is our A and this input is our B. Now connect input A to one input terminal of your AND gate, similarly input B to other input terminal of your AND gate, and similarly take the output from output tab and connect the output of your AND gate to the output. Now to verify the truth table of your AND gate, first of all total number of inputs are 2, so by using the equation that is 2 raised to n, that is 2 raised to 2, which is equals to 4. So to verify the truth table of our AND gate, we have to give total number of 4 input conditions. Now first input condition is when A equals to 0, B equals to 0. Now when A equals to 0, B equals to 0, for this condition our output, that is Y equals to 0. Similarly when A equals to 0 and B equals to 1, for this condition also our output Y which is equals to 0. Similarly when your A equals to 1 and B equals to 0, then our output is again equals to 0, and when A equals to 1 and B equals to 1, then our output is high. Means from this truth table it is clear that as we know the Boolean equation for your AND gate Y equals to A dot B, means it performs the logical multiplication, and from this truth table we can conclude that if all the inputs to the AND gate are high, then and then only your output will be high. And if any one input to the AND gate is low, then your output is low. Now, this is all about the truth table of your AND gate. Similarly, the next gate is the OR gate. Now, we will make change, just click and delete your AND gate and select your OR gate and connect your input A to one input terminal of your OR gate. Similarly, input B to another input terminal of your OR gate and the output of your OR gate. Now, again total number of 2 inputs and one output. So, total number of 2 inputs, so total number of input conditions are 4, that is 0 0, 0 1, 1 0 and 1 1. And we know the Boolean equation for the OR gate is y equals to a plus b, means it performs the logical addition. Now, let us see the truth table for your OR gate. Now, when both the inputs are 0, now when a equals to 0, b equals to 0, then your output, that is y, equals to 0. Similarly, when a equals to 0, b equals to 1, then your output y, which is equals to 1. Then third condition, when a equals to 1 and b equals to 0, then your output equals to 1. And the last condition, when a equals to 1 and b equals to 1, then your output equals to 1. Means from OR gate we can conclude that if any one input to the OR gate is high or 1, then your output is compulsory to be 1 or high. And if both the inputs to the OR gate are 0 or low, then and then only your output will be equals to 0. Similarly, the next logic gate, that is your, now these are all the basic gates. First one is your inverter, that is NOT gate, then second one is your AND gate and third one is your OR gate. Now, let us take the truth table for your universal gates. As we know, there are only 2 universal gates are there, that is NAND gate and NOR gate. Now, let us take the truth table for your NAND gate. Again, connect input A to one input terminal of your NAND gate and input B to another input terminal of your NAND gate and your output to your output, that is X. And we know the Boolean equation for your NAND gate is y equals to a dot b whole bar, means that indicates the inversion of your AND operation, means the truth table for your NAND gate is exactly opposite to your AND gate, because the conclusion for your AND gate is that if any one input is low, then your output is low, and if both the inputs are high, then and then only your output will be high. But exactly opposite for the NAND gate. Let us check. If a equals to 0, b equals to 0, then output equals to 1. Means this condition concludes that if all the inputs are low, that is when a equals to 0, b equals to 0, then your output is high. But in case of your AND gate, when your a equals to 0 and b equals to 0, your output will be equals to 0. Similarly, for the second condition, when a equals to 0 and b equals to 1, then your output is again high, because for NAND gate, if any one input is low, then your output is high. Similarly, the third condition, that is when a equals to 1 and b equals to 0, then your output is high. Again here b equals to 0, that is why your output equals to 1 or high. And the last condition, that is when a equals to 1 and b equals to 1, then your output equals to 0 or it is low. Means this condition states that if both the inputs to the NAND gate are high or 1, then and then only your output will be low or 0. It is exactly opposite to the AND gate. That is why NAND gate is nothing but what? The inversion of your AND gate. Means if you see the truth table for your AND gate and NAND gate, then you will get idea, that is the truth table for your AND gate and NAND gate are inverted version of each other. Similarly, let us take the truth table for your last universal gate, that is NOR gate. Again, what is meant by NOR? NOR is nothing but what? Not OR. Not OR means the truth table of your NOR gate will be exactly opposite to the OR gate. Now, for OR gate, as we know, our OR gate performs the logical addition, means if any one input is high, then your output is high. But now let us take the truth table for your NOR gate. Now, first condition, when a equals to 0, b equals to 0. Now, when A equals to 0, B equals to 0, then your output equals to 1. Similarly, when A equals to 0 and B equals to 1, then again your output equals to 0. Similarly, the third condition, that is when A equals to 1 and B equals to 0, then your output is again equals to 0. And the last condition, when A equals to 1 and B equals to 1, then your output which is equals to 0. Thank you.